In this video, we'll talk about linear motion and speed in terms of how they can be thought about in terms of derivatives and how we can use derivatives to help us talk about these concepts. So the main point of the idea is that derivatives can be thought of as expressing the rate of change of a function. So if we go back to our definition of derivative, this expression here on the right is the sort of average rate of change of the function over the interval from x to x plus h. It looks at how much it changed, the difference of f at the endpoint minus f at the starting point, and then divides by the length of the interval. So when we take this interval smaller and smaller and smaller, we can then think of the derivative over here as the instantaneous rate of change of the function f, because it's the limit as length of the interval goes to 0 of the average rates of change. So in terms of linear motion, what does that give us? Well, in general, we'll have our function s of t being the position of some object. Well, then what's that derivative? Well, s prime of t should then be the rate of change of the position. What is the rate of change of position? Well, it's how fast the position is moving over time. This is the same thing as the velocity. And if we continue, s double prime of t should be the rate of change of velocity, which is how fast the velocity is changing, which is acceleration. So we can get both velocity and acceleration out of a position function by differentiating it once and twice respectively. As examples, so you have an ant that walks along a string, and the position is given by the formula s of t is t cubed minus 6t squared plus 10t, where t is in seconds. Part 1 asks, where is the ant located at t equals 0? Well, it's acting for the position value at 0, so that's s of 0. If I plug in, that gives me 0. At this moment, how fast is the ant moving? For this, I want the derivative at 0. So s prime of t as a function is going to be 3t squared minus 12t plus 10. Therefore, at that moment, which is the moment when t equals 0, the velocity at 0 is 10, which means it's moving at a rate of 10 millimeters per second, because those are the units defined in the problem. And it's moving to the right, because this is going in the positive direction. It's going in the positive direction on the axis, so it's going to the right. At this moment, is the ant speeding up or slowing down? So speeding up or slowing down is asking questions about how is the velocity changing, so it wants the second derivative. So with s prime above, the second derivative, s double prime of t, is 6t minus 12. So s double prime at 0 is negative 12. This would be in millimeters per second squared. How do we interpret that? It's going in the positive direction to the right, but its acceleration is going to the left, to the negative direction. So this says that it's actually slowing down at this moment in time. Why? It's slowing down because the velocity and the acceleration are in different directions. If these had been both positive or both negative, it would be speeding up or getting faster, but because they are one positive and one negative, it is slowing down. How would you answer the same questions about t equals 5? Well, now that I have formulas for these derivatives, I can just plug in the value of 5 and see what that gives me. So I get s of 5 would be the position, s prime of 5 would be the velocity, and then I would say that this is speeding up if the velocity and acceleration have the same sign, and slowing down if they have different signs. You can answer the same questions for any point of t just by plugging that number in for t instead of 0 or 5. Another situation where this applies the idea of motion under gravity. So this is an object that is either dropped or thrown, and is allowed to free fall under gravity and the path it follows. So there's differential equations work that can go into solving what this should actually be, but under ideal circumstances, the position is the following. We would know that s of t is s0 plus v0t plus 1/2 gt squared, where s0 is the initial position, v0 is the initial velocity, and g is the acceleration due to gravity. If you're doing this on Earth, g is 9.8 meters per second squared, or around 32 feet per second squared, depending on which units your problem's in. these values sort of make sense. If I just plug in t equals 0, the value I get for s is s sub 0. Great. If I take the derivative, the s0 goes away, and the v0 sticks around. When I plug in 0 there, this would be the velocity at 0, as expected, or s prime at 0. And the acceleration would end up being g, constant. Let's see an example using this. An object is released from a height of 20 meters. How fast is it moving when it hits the ground? Okay, so what does that tell us about our setup? Well, we know we're going to follow the motion due to gravity formula. What do we know? Well, it's released from a height of 20 meters. That means S0 is 20 meters. What else do we know? Well, we're told it's released. It's not thrown or pushed or moved in any way. It is just released, which means it has no initial velocity. It's still, and then it's let free. So V0 is 0. So that means my actual position function, S of t, is 20 plus 1/2 gt squared. I'm told to use g as 9.8. However, the important thing to realize here is gravity always pulls it downward. So gravity is in the opposite direction of the 20 that is the height. So what I want out of this is 20 minus 4.9 t squared. The 4.9 is because that's 9.8 over 2. I want to know how fast it's moving when it hits the ground. That means I need to know when does it hit the ground, so I can put that into a velocity equation to figure out how fast it's moving. So when does it hit the ground? Well, that happens when s of t equals 0. So I can put a 0 in here. And I get that 4.9 t squared equals 20, or t equals the square root of 20 over 4.9. Now I want the velocity at this time. Well, my velocity should be s prime of t, which, since s is 20 plus 1/2 gt squared, is just g times t, or negative 9.8 times t. Now I can just plug in my value of t to get my answer. S prime at the square root of 20 over 4.9 is negative 9.8 times the square root of 20 over 4.9. That's about 19.8 meters per second downward. That's the idea of linear motion, how it applies to using derivatives, and how you can talk about falling objects using the same setup as well.